I don't need to repeat my title again. So yes, on Wednesday I have provided a training session which is about surface coupling and FSI program with preCICE. So some of you might have known this, but what's different about this talk is about doing partitioned multi-scale simulation and what is that is volume coupling with preCICE and OpenFOAM as one of the solvers. Let's start. So what's motivating us to do this kind of to develop in this direction? The first big application field would be the pulse media field. In the first image, we can see that there is a two-phase flow, which is composed by a solid and gas phase. And this flow would flow through a rocky solid area. This is quite a common occasion when we want to, for example, inject or extract gas from the reservoir. And in this occasion, there are critical spores with three-phase interactions. And if we want to model this physical phenomenon, we want to do multi-scale simulation, because otherwise we need to use pore-scale resolution for the whole field, which is very expensive. And the second image showed multi-scale modeling of a lever. So we have the organ structure, and if we look closer, we can see the macroscopic structure, which contains vine and sinusoid structures. And if we look even closer, we can see the fluid. We can see the vessels, which has blood flow through the liver solid. And actually, we have one application in our group, which is a muscle modeling. It's a multi-scale coupling of muscle itself and the fibers. But some of you, if you have want to do pulse media simulation with OpenFOAM, you might have known that there are already tools like preCICE and also the explicit porosity source that you can use to describe the general pulse media structure in the macros without using real microscale simulation. But then you might ask, why do I need to use preCICE? The answer from me would be that we allow more flexibility and provide features to improve the efficiency of this coupled simulation. And also, pulse media is only one of the many possible applications for this multi-scale feature. So first, I'll give a very brief introduction to preCICE. So it's a coupling library for partitioned multiphysics simulations. For partitioned, we mean that we simulate the different physical phenomena with different solvers, and we couple them together instead of putting all of the stuff in one huge equation system. And preCICE will do the communication between the different solvers, and it do data mapping between shapes of different shapes, and it provides a lot of different coupling schemes to control the flow of the coupling program, and it can do time interpolation when the participant solvers have different time step lengths. And usually the CFT solvers like OpenFOAM and FEM solvers like DO2 or Calculix, they would use an adapter to communicate with preCICE. But if you have an in-house solver, you can also directly call the API functions provided by preCICE. And yeah, this is how preCICE is working basically. And I show here two typical applications for preCICE. The first one, you might have been very familiar with it. So it's a two-phase flow. It shows the deformation of an elastic flap inside the two-phase flow. And the second image is a volume coupling. This rectangular is actually the macroscale shape, and at the position of these spheres, we do one microscale simulation. So this sphere is not a geometry of the microscale simulation. It only means that there is one microsimulation here, and we get the porosity from the microscale here, and yeah, and we solve the heat conduction in the macro phase, which is have some relationship with the porosity. So but for people with OpenFOAM, they would also thinking, okay, I have OpenFOAM already. What can preCICE provide for me? And the first application is a very classic benchmark case. Is a flow around the elastic flap, and the example here is a coupling of 3 participants, which is actually 2 fluid solvers for the outer and inner fluid, and 1 solid solver for the heat exchanger itself. And this is also a 3 participant coupling, which is a controller, the spring, and the flow. So with preCICE, OpenFOAM can do a lot of more stuff than it can originally do with one single solver. But before I start with the introduction to use OpenFOAM and preCICE for volume coupling, I should say that we have far less experience in using OpenFOAM for volume coupling than for surface coupling. And the following examples shown here are only to show the concept is not for physical validation, because the equations used here are quite arbitrary. So at first, I want to start with this example. I have a macroscale field like this rectangle, and in every fillet volume inside this square, I want to do 1 microscale simulation. And the value I want to send from the microscale to the, which is called the source velocity, to the macro fluid solver is velocity. So how should I set up this coupled program? At first, for macroscale, we use OpenFOAM. So as we always do for using preCICE and OpenFOAM adapter, we first add the adapter as a function object, which we'll call preCICE lib, and then we configure the coupling in OpenFOAM with system / preCICE dict. This contains the information to tell OpenFOAM what kind of information I want to communicate and where I want to exchange this information. I want to do a volume coupling or do a surface coupling. And third, we need to configure source term. This is because we want to write the velocity into OpenFOAM, and if we don't use a source term for it, it will be overwritten later by OpenFOAM. So we use a coded source to take this reading velocity into account. And for microscale, we use Nucleus. So this is basically the same as we do surface coupling with OpenFOAM and Nucleus. First, we import the preCICE library, and then in the main function, we create a preCICE object, set the coupling mesh and data, and then we continue the coupling by solving the PDE and write data to the macroscale, and then after runtime, after total time is over, we finalize the coupling. So this is basically the same as we do for surface coupling, except that we want to do volume coupling inside the preCICE dict. But preCICE itself also has a tool which is specially designed for multi-scale simulation, which is called a micromanager. So this is a thing between preCICE and a group of microscale simulations. It's not between preCICE and one specific multi-scale simulation. And this tool is mainly developed by Ishan Desai. And so next I will briefly introduce what features this micromanager have. At first, it can adaptively run the microscale simulations. So from this image, we can see that there are active microsimulations and inactive ones. This means that for each iteration or each time step, we only solve part of the microsimulations, which have a very different status than other ones. And for the inactive ones, we copy the values from the active ones, which is very similar to it. And we compute this similarity with some algorithm, and this is also configurable in the micromanager configuration. So with this adaptivity feature, we can save a lot of time, because usually in porous media application, we have a large amount of microscale simulations, but most of them have very similar status, and we don't actually want to solve them one by one. Yes, so this is a macrofield of temperature, and this is a here are the positions with the microscale simulations, and the black spheres are the active simulations. And this is actually showing how many times this position have been active. So obviously, these four spores are very representative for the whole field. And that means we use almost 5 microscale simulations to represent the whole 32 microscale simulations. And then micromanager also can do parallelization for large amount of simulations, which means that it puts the microscale simulations onto different processors instead of put each microsimulation onto different processors, because usually one simulation is very fast and we have a large amount. We don't want to parallelize every simulation. And it also provides some assistance by diagnosing, which means that you can very conveniently write some values from the microsimulation to inspect the status of your simulation. So now with this, we want to do a multi-scale coupling. It's a bit more complicated than the previous one, is that we want to send the pressure gradient from the microfluid to the micromanager, and we want to rate the velocity and send the velocity in the reverse way. So to write the velocity from the microscale to macroscale is still the same as we previously do, but we send the pressure gradient now, and the geometry is still the same as previous one. The area of the burst media has slightly changed, but it's almost the same. So at first, because we want to write pressure gradient, we add a function object to calculate it in OpenFOAM. And I write here that it should be in front of adapter because I think the function objects are executed according to the sequence you write it. And then because OpenFOAM, the adapter itself currently doesn't support you write pressure gradient to preCICE if you are doing a volume coupling. So you need to do to do the extension by yourself. That is, you tell OpenFOAM that if I'm doing volume coupling, I want to write the pressure gradient to the buffer for these cells in the cell set I selected. So it's quite straightforward. And also to extend the extension of the adapter is quite common actually, because this adapter only provides some common used features. And if you want to exchange some unusual values, you need to extend it a bit, but it's quite easy to do. And then we configure the microscale simulation. First, we need to refactor the microscale code a bit, because the micromanager has a special requirement. So we have a class which is called microsimulation, and we have the initial function and solve function to really solve the PDE, and we have the get state and stat state function are used to do checkpointing, because if you want to do implicit coupling, you need to store the values you want to reuse when you repeat this iteration at the beginning, and set state is to load this state into the microscale simulation. So for me, for this simulation in the solve function, I simply use the Darcy's law to compute the velocity in the x and y direction from pressure gradient, which are read from preCICE. And then we also add a configuration file for the micromanager, which contains the name of the main file of the microscale simulation and the coupling parameters and the simulation parameters for the adaptivity or parallelization, etc. And in the end, we can get this kind of coupled simulation. We can see that in this area, I have a micro simulation, and it's this flow and this streamline show show that the coupling is happening. But how physically true this flow through porous media felt is I couldn't promise. And I also write here for 250 time steps, the serial run with adaptivity cost. Sorry, it's reverse. Without adaptivity is 170 9 seconds, and width it is 127 seconds. And the parameters are not fine-tuned, so this is not the best you can gain from it. Okay, so next, now it comes to a conclusion. First, we said that we can do general volume coupling with preCICE now, and we can use OpenFOAM as a macro scale solver. But because we have been doing this for quite a short time, so there are still a lot of possible future work. First, we want to build multi-scale model for turbulent flow. It's turbulence because it's a very interesting topic for fluid person. And if possible, we want to use OpenFOAM as microscale solver because it provides a lot of features we can use too. And we also want to use surrogate models for microscale simulation to spare computational cost further. And here is my email. If you want to contact me, please note it down. And yeah, thank you for your attention. And I'm here for your questions and feedback. Thank you very much.
Thank you. Any questions?
Thank you for your brilliant presentation. I'm quite interested in the multi-scale model for turbulence flow. So I'm wondering, is there do you think that machine learning method aided multi-scale turbulence flows solving in your in your code is possible in the future?
Yes. So the machine learning can be used to do this surrogate model. And of course, you can also use it for...
Can you put some several methods for the compile to finish these problems?
I'm not doing this research right now, so I couldn't tell. But I think at least there is one research that they learn the you can learn this
source turn.
You can learn this model like the easiest way is that if you only want to do one type of multi-scale simulation for you, because it's important for you, and you can always do external learning and keep a table of the microscale simulation, the input and output, and do some interpolation. This is a most obvious one. And also you can try to learn some parameters during the simulation. But yeah, then it depends on what kind of parameters you use and how much time it would cost.
Thank you. Thank you very much.
Thank you.
Any more questions?
Hello. Yeah. Thanks for your nice presentation. But really, I have a small question. You mentioned again and again about this micro scale modeling, but really, I didn't understand what you modeled. What do you mean by this macro scale modeling?
So it's like a flow through a channel which has a porous media field, and in this field, the permeability is lower, so it has more resistance to flow through. And in each finite volume inside this area, I do one microscale simulation to tell you if you have this pressure drop, how much velocity you can get.
So it means you are modeling the multiphase flow in the porous media, or?
It's not a multiphase flow, it's only one phase. But yes, it's through a porous media.
Imagine if you have irregular porous media and you want detailed answer for directions, you get different pressure drops, right?
Yes.
So by simulating the microscale, you can get the pressure drop in a particular direction.
Okay,
yes,
yeah.
So
this is quite different from us. Okay, yeah. Anyway, I know.
Yes, it's the first time we introduced this in the workshop. And if it's a one-phase flow, it's quite actually, and if it's a very simple porous media structure, you might represent it with a formula directly without solving the microscale. But for example, you have a two-phase flow, and you really want to describe every physical phenomenon that happens in the microscale. You want to really do the microscale simulation, then you do multi-scale coupling.
For multi-phase modeling, always when we are thanks for multi-phase flow modeling, when we are talking about multi-scale, okay, macro scale, okay, always it implies it DNS either WOF from tracking or level set, and meso scale is always Lagrange. Yeah.
There are a lot of methods to approximate this microscale simulation in macroscale.
Thank you. Last question.
I just want to get some feeling about communication costs. Typically, for your example, how much time costs because this coupling, your technique, communication percentage of communication time for communication.
I didn't check the time providing for this simulation in detail, but usually the communication is quite fast because in preCICE there is a very efficient peer-to-peer communication method, and normally the simulation time is the major part.
Okay, for this example, and also, do you have a feeling if we do the massive simulation, especially on the microscopic scale, then you need the scalability? Yes. I don't know whether you have an example to show. You use this technique, you have a very good scaling.
Yesterday I want to find some data about which describe the scaling of the micromanagement tool, etc. But I didn't really find the published information about it. But currently we are actively working on the prioritization of it and increase the scalability. And currently it could be used on cluster for, I think, at least 10,000 cores, etc. But I don't remember the real number.
Let's thank you, Jen, again. Thank you very much.